It's noon. We're going to go ahead and get started so we can get this thing closed out by the end of the hour. So welcome to Innovation Insights. Innovation Insights is our new webinar series. Just to explain what that is. Features products and technologies from our industry members, which you'll hear from 2 today, and our core R&D partners, which you'll hear from 1 today. We'll do this monthly. So presentations typically from 1 small company, 1 large company, and 1 research partner, which a research partner is typically universities or national laboratories. My name is Brosius. I'm the Chief Commercialization Officer for IACMI, the Composites Institute. I'm also the Executive Director of the IACMI Consortium. At these monthly meetings, IACMI members in good standing, or those who have a membership agreement on file and have paid their membership fees, are eligible to present. So if you're an IACMI member and you're interested in getting into this schedule, contact me to do so. So the idea here is to not feature technologies that have been around for 30 years, but to talk about relatively recent technologies that you may not be aware of, including some innovative uses of technologies that might have been around for a long time, but have found some more novel ways of helping us lower costs, speed up processes, and improve products. A little bit about IACMI. We offer with 3 main themes we call convene, connect, and catalyze. So that's bringing people together, connecting those people with solutions, with people with questions, and then to catalyze innovation within the ecosphere of composites. So these are some of the product offerings that we do bring to the equation. We have facilities, open access facilities, technical resources and models for using those facilities, for engagement, with large consortium, approach to achieving, goals of the Department of Energy, work in materials processes, digital tools, and then talent development through workforce development. We are what we believe to be a very connected community. Here are some pictures from previous members' meetings and other visits that have brought the industry together. So if you go to our website, iacmi.org, you can find out information on how to become a member. So we're going to go ahead and get started with today's presenters. Our first presenter will be Andrew Maxey. He's the CEO and founder of Vartega, which is a recycling company, carbon fiber recycling company, and a small and medium enterprise. So that'll be followed by Dr. Ramki Subramanian, who's the managing director of DowAksa USA, and then Professor Doug Adams from Vanderbilt University, who heads up the laser lab at Vanderbilt and expert in non-destructive evaluation. He's got a very interesting presentation on use of thermal imaging in ways that you might not have thought about before. So with that, Andrew, I'm going to hand the stage over to you if you want to go ahead and share.
Excellent. Thank you so much, Dale. I really appreciate it, and appreciate the invitation to present to all of our friends at IACMI today. It's been a long time since I've seen many of you in person, but I'm hopeful that we'll be able to connect again here shortly as we get into CAMX and other meetings here in the future. As Dale said, my name is Andrew Maxey, and we founded Vartega, myself and several of the co-founders, back in 2014, but got really serious about it in 2016. And that's about the time we joined IACMI. So really appreciate all the hard work that the folks at IACMI have put into building such a great environment and ecosystem of partners, many of which we've worked together on different projects. So thank you to all of you as well for your support in those efforts. At Vartega, we're making carbon fiber more accessible to more industries, and we do that with recycling. So I know many of you have heard about the type of recycling we do. I'm just going to touch on that a little bit, and then want to share some specific applications that we've been working on that we think are really cool. And then Dale can correct me, but maybe we can have some questions there as well at the end if there's anybody that would like to dive in on anything. The driver for us is sustainability, And sustainability is an interesting topic that has been really in the news lately. We look at it through sustainability of our business. Economics always drive business, and the economics of recycling really have to make sense for the sustainable environmental aspects to make sense as well. So, as we talk about decarbonizing the future, that's a bit of a buzzword right now, but it's through lightweighting of vehicles, it's through replacing energy intensive materials like virgin carbon fiber, and replacing metals as well. We're really excited about the work that's happening, the accelerated work that's happening, especially over the past year amidst some supply chain challenges to accelerate the adoption of recycled carbon fiber. The opportunity that we've been most focused on is the automotive industry. And I know many on this call are intimately involved in that as well. And that's because the opportunity is so large for lightweighting, especially as we electrify vehicles and need to extend vehicle range. A significant extension in range, so 10% weight reduction can result in a 6 to 7% improvement in efficiency, and even as much as a 10% extension in range, depending which study you're looking at. But the cost of carbon fiber has historically been prohibitive for that. So recycled carbon fiber at half the cost makes a significant opportunity there. And it's a big opportunity because fiber reinforced thermoplastics, which is where we focus, is a very large market, traditionally dominated by fiberglass, but at the right price point, carbon fiber can make a ton of sense. Probably not telling you anything you don't know, but to recap, the opportunity, of course, because carbon fiber is expensive, but also the scrap rates are very high. So the amount of recycling is increasing, which we're very excited about. Scrap rates are decreasing, which is also very good, but the adoption of composites means there's a bigger and bigger waste issue every year. So it's important that we tackle it. Our strategy for that is through a series of growth steps that we've established for ourselves, and that we've been able to demonstrate through our collaborations with IACMI partners and projects. Early on, we developed a chemistry-based recycling process for the recovery of uncured prepregs, and we've actually got significant IP on that, which you'll see in the next slide. But what we realized as part of our customer discovery, working with folks, especially in the automotive industry, and through our collaborations through IACMI, is that the form factor was really important, and getting the carbon fiber into a format that is easy to feed was really critical. So we've done that now, and are selling that commercially today. We do that not only for our customers through recycled carbon fiber sales, we also do that for customers that may have their own scrap that they'd like us to recycle. That's a big part of our growth that we've experienced over the past couple of years. We will continue to deploy our recycled prepreg systems as well, the hardware as a service, as you see here. And we've also shown that we can recycle other advanced materials, which is really exciting for the long term. And ultimately, there's a lot more scrap out there that we can help address. So we're working on that as well. I mentioned the IP we have. I don't need to bore you with all this, but we do have patents granted here in the US and internationally, and additional patents pending, which we're really excited about. The key considerations of this are the energy reduction that I mentioned, and also the cost reduction. Now, to get into applications which are fun, this is actually the workflow that you'll see for our IACMI project, our project 6.20, where we had different, and this is also specific to a related project within IACMI to make the fender. So recovering of the prepreg material through our chemistry-based recycling process, you can see kind of a close-up of our reactor, our pilot scale reactor in the upper left. And carbon fiber comes out as a recycled carbon fiber comes out as a big fluffy mess. It's very difficult to work with. So we have developed the process to consolidate that carbon fiber into the bundles that you see in the upper right. And as I mentioned, it's critical for to get that to feed well. And there's a lot of different variables that affect that. But imagine, if you will, trying to feed through a 3 or a 4 inch circle, get that material to flow. And that's essentially what we've done with our bundles. That gets compounded into thermoplastics. And in the exact scenario for our project, we actually recovered some prepreg that were made at the surf. That was a DowAksa project. We then did our conversion process, used Michelman sizing, an IACMI member, and optimized the sizing for the chemistry that was going to go into. Techmer then did the thermoplastic compounding for us, and the material went back to the SURF to make the injection molded part, which was this fender. They have a new tool in there that we're actually working on right now, and I apologize because I meant to include a picture of that, but it's a seat back tool that's got a really interesting geometry that the folks at the SURF can tell you more about. And we're excited to hopefully shoot parts in there in the next month. So they've been working hard through a whole bunch of challenges amidst COVID, but making good progress on that. The key again, metals replacement. So whether it's this fender or the seat back, replacing steel, and also in other cases, aluminum and magnesium for cost reduction, well, weight reduction, and then if you do it right, also getting some cost reduction, which is a big benefit. Some additional applications that we've been working on that are a lot of fun, some other automotive components, structural components, but I want to really focus this conversation on some new products that just launched. The 3D printing filament with Braskem that you see in the upper left there, that just launched a couple weeks ago. That's a polypropylene reinforced with recycled carbon fiber. Amazing properties, I'll show you that here in a second. And then in the lower right is a bicycle wheel by a company in Michigan called Encore Wheels using our sustainable carbon fiber to replace their virgin carbon fiber. So both just amazing applications. That's in a nylon in the lower right. But let's spend some time talking about the Braskem filament. And I'm going to attempt to play this video. If it doesn't work, you can find it on YouTube on Braskem's website. But it's a short clip, so we'll just watch this really quick. All right. So what's so fun about that is for anybody that's done any 3D printing with polypropylene, polypropylene is a great material, low density, really good performance and applications, of course, in automotive and consumer products, consumer electronics. But it's historically been very difficult to print with because of some warpage challenges. And what the carbon fiber does actually reduces that. The reinforcement provides more stability in the polymer at the loadings they've got it. And you can see the part properties here. The density is still really good. In fact, it's amazing that it's got that density. And the strength and stiffness are also very good. I think it's a 6x increase in, I think in strength. I don't remember exactly if that's strength or modulus, but very good properties. They're very excited about this. It's commercially available now through M. Holland. That's their distributor. So I share that with you because this is just a fun application that has so many opportunities, not only just in traditional additive manufacturing, but they're really focusing this product on manufacturing and automotive and aerospace applications where you may not have thought of using material like this before, but it's an amazing product. And the other cool thing that we're really excited about is actually our take back program. It's our filament recycling program. And there are other filament recycling programs out there, but this is the first one that I'm aware of that actually closes the loop on the supply chain. So Braskem, we supply the carbon fiber to Braskem, and then obviously it's made into the thermoplastic compound and then the filament. They do the distribution, but customers, when they have a failed part or they have just scrap material, can actually send it back to Vartega and we'll recycle that and be able to incorporate that back into the supply chain. So this is just a start. There's a long way to go, obviously, to create true circular supply chains in the composites industry, but this is a fun one that we think is going to make a big difference going forward. So close out my thoughts there on the Nebraska material, we've done other 3D printing with nylon. We've done some interesting work, or doing some interesting work with wind energy, turbine blade recycling, incorporating into additive manufacturing materials, and worked with other partners here locally as well. Steelhead Composites several years ago. You remember the composite overwrap pressure vessel we made with recycled carbon fiber was very exciting. And then we're working with a musical instrument company as well to reinforce certain parts in their instruments, which has some benefits that we hope to share more here in the future as well. So ultimately, that culminates. All these case studies and applications are great because they show the viability of recycled carbon fiber in these materials and in these applications. But I'll come full circle to talk about the automotive industry, where we really think we make the biggest difference because that lightweighting. And this is a pro forma we share about our impact, because for every ton of carbon fiber that we recycle, we actually reduce CO2 emissions by 13.4 tons. And then if you use that recycled carbon fiber in an automotive application for lightweighting, the lightweighting benefits over 47, it's almost 48 tons of CO2 greenhouse gas reduction. So that's really the big bang for the buck. And that's one of the things that IACMI has done a great job of, is focusing on applications where you can benefit from the lightweighting. Obviously, the recyclability aspects of IACMI from the very beginning, but the Department of Energy has also had a very strong focus on how do we make vehicles more efficient. And it's an amazing thing to show that with recycled material, you can not only lower the cost, but also lower the embodied energy. And one of the greatest takeaways that Dale actually taught me was that when you look at it, you look at the LCA that we've done on this, the recycled carbon fiber actually has a lower embodied energy than the virgin polymer, the virgin nylon that it's going into. So the more recycled carbon fiber you put in, the better off you are overall. So we'd like to use more and more recycled carbon fiber to help lightweight vehicles and reduce those emissions, and support folks that want to work with us to do that. So I'll end my comments there and stop sharing. And then I don't know if it's appropriate if we have a couple minutes for questions. Otherwise,
we do have a couple minutes, Andrew, and we have a couple of questions. So I've got one asking if the recycled carbon fiber has to be resized after going through the recovery steps. Great question.
The answer is actually no, it doesn't have to be, but it's really difficult to work with if it's not resized. So that's a big part of our process, is putting the right compatible binder on there, the right sizing on there. And as mentioned, we work with Michelman, we work with other sizing suppliers as well to find that right chemistry for the application, whether it's polypropylene or polyamide. And if a customer has a certain sizing they would like to use, chances are we've already tried it, but we're always open to exploring new chemistries as well. And I'll clarify, the reason for that is to improve the feedability and the handleability, so it's not fluffy and difficult to work with.
All right, and I have another question here. Is in order to decrease cost, have you done any work with combination of carbon and glass fiber?
That's a great question. Vartega has not. We don't do compounding at that scale. We have some capability, but hybrids are certainly a thing, and some of our customers have explored hybrids. I can't share specifics around what they've been doing, but yes, you can combine carbon fiber with all sorts of different reinforcements and other additives to tailor your properties the way you need to.
Okay. You'd indicated, given kind of percentage thing, cost delta between recycled and virgin carbon fiber. I think you had said about 50% reduction.
Yeah, that's right.
Okay. And then last question before we move to the next speaker, what obstacles are present that would prohibit growth of Sovolysis? And I'm thinking the speaker may be talking about, regulatory or cost or otherwise, and how we overcome those.
Yeah, that's a great question. And there, cost and regulation are always considerations. What the recycling industry has done a really good job of is there's some incumbent technology in pyrolysis that's worked really well for cured composite and and other feedstocks as well. The timing is actually a big part of it. I would say that that's the biggest challenge that we face, is just market readiness for that level of recycling. And there are all sorts of different feedstocks that we source, and certain feedstocks are easier to get into product today than others. So I would say, yeah, timing is the biggest one. I mean, we can talk about the regulatory. It's actually not that big of a concern with our system. There's considerations on permitting, of course, and depending on what municipality, there are certain requirements there. But because we built a modular unit, it's self-contained, we recycle our chemistry, so it's really, really beneficial in that regard. But you know, like any new technology, it takes validation, it takes demonstration, and case studies, which, as I pointed to today, I think what we're seeing is an appetite for more recycled carbon fiber, more recycled material, and I think that's going to drive that demand to overcome, you know, whatever challenges exist for chemical-based recycling or thermal-based recycling, even mechanical recycling. The need is there for those materials, and you know, the other thing to consider is just scale. It takes time to get up to a certain scale, and then the economics usually take care of themselves. So hopefully that answers that question. I kind of dragged on there a little bit.
That's all right. Okay, thanks for presenting, Andrew. I know people can reach out to, you know, find you on the website at vartega.com.
That's
and
right.
If, or they can reach out to us and we will put them in contact with you.
Excellent. Thanks, Dale. Thanks, everybody.
All right. Thanks, Andrew. Okay. So our second speaker is Ramki Subramanian from DowAksa. He's the Managing Director of DowAksa USA. Ramki, go ahead and share. Get started.
Nothing, Dale. Thank you very much for the opportunity to talk to everybody. Friends, very good morning to you all. Hope you're all doing safe. I want to share a few slides with you to introduce DowAksa and our XForge materials over here. And basically, you know, first and foremost, you know, appreciate what Andrew talked about. I think this is really important. And as part of our growth of carbon fiber, we also completely support all opportunities to close the loop and make sure that we leave the world a better place to live in. And we'll talk a little bit about what we are trying to do as well in the following slides. First and foremost, DowAksa is a 50-50 JV between Dow Chemical. Most of you should know Dow Chemical, and Aksa, which is a Turkish company. They are the world's largest producer of acrylic fibers. So this JV was formed primarily to leverage the strengths of both these companies. And this is kind of what we'll be talking about. Our key focus really has been to work on cost advantage carbon fiber and downstream product offerings, but do it at scale, you know, because that's really our core focus area. This photograph on the left top is our site in Turkey. This is in Yalova. It's about 80 miles away from Istanbul. And the reason I'm showing this, the red shaded area is our carbon fiber facility that was carved out for the JV. And the rest of it is really the acrylic facility of Aksa. So you can see that we are a fully integrated site. We don't make acrylonitrile, but we make everything else from down there. And this slide on the right-hand side is our warehouse for the pultruded laminate that we, polyurethane-based laminate that we make for the wind industry. But I wanted to share that with you because this also demonstrates that, hey, you know, we not only do that at scale, but again, at the end of the day, it's all about economics that Andrew has mentioned earlier. What is the impact of the cost, focus on cost? At the end of the day, we are looking at displacing metal. And this is just a schematic. The idea is how do we reduce the gap between metal and carbon fiber composites, and by looking at it holistically, not just as a material, but also working on key aspects of costs related to conversion. And again, a very important one, that is the how do we deal with the waste? And this is especially true when you think about thermoset materials. And we are looking at it holistically and making sure that we address all aspects of this of this problem and not just look at the cost of the fiber alone. And we look at chemistry as being the key enabler. But before we go to chemistry, I wanted to share with you the journey that DowAksa has been through. And this is basically, we started off, this is AXA, started off in 2006 in small scale. But now we are at about, we have 2 production lines. We are focusing primarily on industrial grade. We started off with a 24K, but now we're going to focus more on a 30K product. And we're looking at maximizing the productivity from these lines, right? And we're now at about 6,000 tons of carbon fiber. We're looking at some serious expansion plans. We are currently sold out, but we are looking at a third line so that we get close to about 10,000 tons of total carbon fiber. The chemistry-based offerings, apart from the carbon fiber and the fabrics themselves, are what we call XForge. This is what was done earlier when we started off with the Dow and Ford project. This is based on water fuse chemistry from Dow Chemical. So we have the license for that, and we've demonstrated that we can actually do this at scale. We are setting up our commercial line in Michigan as we speak. This should be operational towards the end of the year. And the other product is the laminate that I talked about. This is the polyurethane pultruded material. And we'll talk a little bit about both of these in the coming slides. And we are slowly now expanding our portfolio to get into the thermoplastic-based compounds as well. This is the nylon-based materials that we'll start with, but we are kind of chemistry agnostic, so we're not tied up with nylon. So this gives you, a lot of you will probably know this, this slide in terms of the benefits of carbon fiber-based composites from a specific strength and specific stiffness perspective. This is to show that we kind of span the range of performance. This is our XForge and XForge. So XForge is basically the preg made with unidirectional fabric, and the XForge is after you kind of chopped it up and put that into a mat. That gives you some strength in the Z direction also. Of course, you lose some performance compared to the unidirectional fabric, but this has got certain specific advantages, in giving you, what shall I say, performance in molding and parts that are very difficult to do otherwise. And XPAR is our laminate. So this is about as close to the pure carbon fiber performance as you're going to get. This is about 70% all carbon fiber by volume. So the business case for the laminate is well proven. We have several large OEMs as our key customers, and the carbon fiber is actually in the spar cap. So that is a spinal column, if you will, of the wind blade. And this cartoon gives you the perspective on size of these materials, right? So we are looking at anything over 70-meter tall blade. It's typically going to need a carbon instead of glass, and primarily because of the weight saving. And this helps. And this is going to be even more the case as we go into longer and longer blades, especially in the offshore windmills. And the business case is given over here. Essentially, we save really a large amount of mass, and that is the core of the driver for the windmill industry, the renewable energy industry working on windmills to move more and more to carbon spar caps. And as we speak, we are looking at other opportunities for further mass decomposition by looking at additional usage of carbon. We are working closely with IACMI, or we will be working closely with IACMI as we move forward in this area. And the other aspect of this one I wanted to point out, and this is relevant to what Andrew pointed out, we are looking at opportunities of how do we look at recycling and repurposing of these spar caps when we get to end of life. Right now, we still have about 10, 15 years, but we're already looking at aggressively finding options of using these spar caps in additional applications at end of life. And if not, how do we find economic ways of recycling these materials. And any opportunities there are welcome as we look for collaborations on those fronts. The XForge, so this is basically an epoxy-based prepreg. The epoxy, as I mentioned, is the Vartega chemistry. There are a few things of note of this Vartega chemistry in that it is it is room temperature stable, and I say that at about 20 degrees C. It's perfectly stable for several months, and it also has very rapid cure time. So you can make parts in less than 3 minutes. And this was developed in conjunction with Ford, way back a few years ago. And the idea here is how do we mimic the performance of cast aluminum, not only from a mechanical performance point of view, but also from a processing speed perspective. And we've demonstrated that it is stack-free, it is automation-ready, and the business case is in really replacing cast aluminum. So we are working with a few OEMs and tier ones as we speak to see how we can commercialize this and bring it to scale. This has been proven, as I said, at a couple of different scales. But a key aspect of this work was the partnerships that we've developed, both with Purdue. That was part of the IACMI. I think Bruce had given a slide at the beginning when we introduced IACMI. A lot of that work was done as part of this collaboration, and we have the capability now to go from design to prototyping to testing and reduce that speed cycle time significantly. So we have the capabilities, and we are working closely with both Purdue and University of Warwick. This is the Warwick Manufacturing Group in this activity. A couple of technology proof points. This has been demonstrated. This has been shared in the public domain earlier, and we managed to replace a couple of different materials in the metal segment, both that is at the borons for boron steel and magnesium. But we've also shown that we can replace and have good mass saving against glass fiber based SMC. And so these are proof points that have been demonstrated, and we are looking now to collaborate with specific companies as we go forward. And we are primarily focused on automotive, but we are looking at other industry segments as to how we can leverage these materials and demonstrate and bring to market in a quick way lightweighting solutions. Just a couple of slides over here to show that there are many ideas that are out there that we are working on, and we look forward to collaborating with people. This is just a summary over here, but eager to talk to you guys and see where else this can be used. Thank you, and I'm happy to answer any questions you may have.
Thanks, Ramki. When you showed the picture of the spools of the spark cap material in the factory, yeah, what's how much of that are you making right now per year?
Oh, we are in the range of about 8 to 10 million linear meters a year.
Okay. Yeah, all pull true.
And looking to grow that even more.
Of course, yeah. Those are going into spark caps. Yeah, what's the length of those typical spools?
Typically about 350 meters per spool.
Okay. Per spool?
Yeah.
Okay. All right. On the, my also understanding is that the material, the XForge material, or the XF and the XForge, are both have Forge specifications, right?
Yeah, one of them does. The XForge does. The XForge, we are close, but we didn't complete the project at that time. But we do have the specification for the XForge. Yeah.
Yeah. Okay, that's good. Okay. Now, you as part of your product line, do you also offer a chopped fiber format? I mean, I guess a chopped neat fiber. I know that the XForge is a SMC type of mat, but it's got the resin on it. Would the but do you also offer chopped dry fibers?
We do, but that's, that's not our focus because, I think there are going to be case by case basis, but we do have, but it's really not a huge focus area for us.
Okay.
I have some material if somebody needs it, but,
Yeah. So where do you see these materials fitting into the electric vehicle space? Any particular applications in the electric vehicle space?
Certainly. From our perspective, we are looking at structural elements. We are not that keen on aesthetic parts because 30K, it's not going to be very amenable for the kind of looks that you can get with the 12K. But structural performance is where we would focus on. Lots of, as I showed in the slides, many parts that require structural performance. And also, especially in the electric vehicle space, we can bring in structural performance along with the battery case. So we are looking at additional functionality in things like battery cases, where you can combine our laminate material with the XForge. You can have composite structures that provide different kind of capability that is currently not available.
Okay, you can envision protrusion forming a frame and then the XForge or XZForge forming surfaces, larger surfaces.
That's correct.
Okay, it doesn't look like we have any further questions. Again, folks want to get in touch with you, they can reach out to us and we can put them in touch with you.
Absolutely.
Or go to DowAksa.com and find you there.
Okay. Thank you.
All right, thanks, Ramki. Okay, so moving along, our third speaker today is Professor Doug Adams from Vanderbilt University. Doug, are you ready to go? So entertain us.
Thanks very much, Dale. And thanks to the others, Andrew, and for the great talks there. So appreciate getting the chance to at least virtually be with everybody. Look forward to the next chance to see people in person. So as Dale spoke about, I want to talk about novel uses for thermal imaging in large part fabrication. I'll mention the project that we've been involved with in IACMI here in a moment. But of course, all of you familiar with non-destructive testing. It's a technology that has literally been around for as long as we've recorded information about technology. So lots of different ways in which you can do non-destructive testing, trying to assess the material state and in particular presence of flaws without further damaging the material. Obviously, visual inspection remains the most prominent form of inspection, in particular, even in composite parts, that's true. So essentially what we have been looking at in our projects with IACMI are novel uses of traditional ways in which we do inspection. So for instance, I can pass heat behind this composite part simply using a heat source. And I can use a thermal camera on the front side, looking at the front surface of this material, and I can see that there's a geometry change in that material. So if I'm looking for flaws in the material and I've got the camera close enough and the pixels are large enough to be able to pinpoint that flaw, I can use that to do inspection of composites after they're manufactured. But we've been doing this kind of thermographic inspection for decades. So the question is, how could we use this technology in a new way, in a more innovative way? And so when we think about, for instance, large part fabrication, like manufacturing large wind turbine blades, blade spars and the like, we could potentially think about using thermographic inspection during the process. So as opposed to using it after the fact, after we've gone ahead and infused the composite material and cured out that material and inspecting for flaws at that time, what about using thermography during the process? Because after all, these processes come with thermal responses. And so in our project 4.2 led by NREL involving TPI Composites and Arkema and Johns Manville, industry partners, we took a look at this type of technology. And so what we were looking at specifically is working with a new resin system called Elium that Arkema developed for this project. And it's a thermoplastic resin. It has really interesting properties. really complex cure kinetics in particular. And so this particular thermoplastic provided a lot of benefits when it comes to levelized cost of energy for wind turbine blades, including reducing cycle time, reducing embodied energy, and also reducing capital costs. And our role in this project was to try to assess the thermal state of this resin as it cured, and specifically to try to avoid boiling of the resin. And so, for instance, if you cure out a block, a plate of this resin, and you do it properly, this is what it looks like. If you cure it out and it boils, this is what it looks like. Okay, so you get that porosity as the gas is released during boiling. So what we would like to try to do is utilize the heat signature of the curing material in order to ascertain if it's produced flaws, the manufacturing process. And the idea would be to do this in real time, our vision to do it in real time, and then utilize that real-time information to actually fix the process in real time and avoid flaws in the first place, right? That would be the ideal way in which to use this technology, is to avoid flaws. And you could also potentially use the technology to design your process open loop so that the process is designed in such a way that it reduces the potential for flaws. And so what we're doing here is, the key idea in what we're doing is we're using, as I show here in this image, an IR camera to look at the surface of the mold in order to understand what temperature changes we might be seeing in the process, and how those temperature changes on the surface might be able to be used to infer that there might be flaws deep inside the part. And so what we're using is essentially an outlier technique. So we're looking for places where the heat is either too low or too high, indicative of something happening in the process. And so, for instance, on the right here, you see that during one of these processes, we had a hole in the vacuum bag, and we were able to spot that and actually fix it so that we only saw small surface imperfections ultimately in the process. So for instance, this is actually what that looked like during the process. What we saw with our thermographic analysis was this pinhole that had occurred in the vacuum bag, and then here on the right is what it looked like after the process, after we had fixed the pinhole and allowed the process to continue. For the most part, we saw part integrity, but on the surface, we saw some of this snowflaking. So if you're interested in what that looks like overall as the process unfolds, this is what you actually see. You'll see infusion. So initially, actually, you see a temperature change because the resin is at a different temperature than everything else around it. And so you actually saw the infusion process. But then you'll actually start to see the curing process here, starting in the channel and then propagating across the part. You'll actually see kind of a heat wave move from right to left here in just a second. And so what we're looking for, during these processes, there comes the wave. So we're actually looking for anomalies in that heat signature. But you might ask, how can you see? There's the pinhole. How can you see things not just on the surface but deep inside the part? And so that's really what our technology addresses, is the idea of using that surface temperature combined with a model, with a heat transfer model, to actually infer what's happening below the surface. And so what we do is we use a fast computational model, heat transfer model, an inverse model we call it, along with that surface temperature data in order to infer that there's a change for instance, in the heat that's being emitted beneath the surface that might be indicative of a flaw. But the challenge is that the model has parameters in it. And so like all models, these models have errors in them. The data also has errors in it because, like all data, data has errors when you're looking at the thermal response of this part. And so how do you address developing a technique that uses two inputs, to this inverse model that's a heat transfer model, and the thermal data on the surface, when both of those inputs have errors associated with them? So what you can use is what's called a Bayesian approach. So we in particular use a Kalman filter, what's called a Kalman filter. And the basic idea of a Kalman filter is that even if these inputs have errors, you can actually, over time, as you update the model, as you update the data, in other words, as you take new pieces of data, you can actually drive down the error, and in particular, drive down the standard deviation in your estimate. And so that's what I'm showing here. You predict something, you measure something, you compare those two things, and over time, you're able to drive down the error. And what these equations show simply is that you're able to reduce both the error in the estimate, but also you're able to reduce the standard deviation. So you're increasing your certainty in what the estimate is, for instance, of the temperature beneath the surface. So we're using this Kalman filter with the data that we obtained that I showed you earlier, and these are the kind of results we can get. So if we compare, for instance, our estimate of degree of cure of the material with the estimates that you get with thermocouples that are stuck inside this part at different depths, we see this kind of comparison where the degree of cure increases, reaction occurs, of course, very rapid changes in degree of cure, and then it cures out. And so we see very good agreement between our estimate and the estimates that you get within the part with temperature measurements that are being made by thermocouples. But in terms of flaws, what I'm showing here on the right is the ability to detect flaws at different depths in the material. So this is at 1 centimeter deep. These are both 1 centimeter by 1 centimeter volumes that occur beneath the surface. And you can see here, this is closer to the surface up top. This is deeper beneath the surface. And essentially what we're doing is we're simulating flaws using a % volume fraction of fiber to simulate the possibility that you have more or less resin in those pockets. And you can see that even as you get deeper, we're able to see the flaw and we're able to see those temperature variations that would potentially produce, as I showed you earlier, flaws in this material. So, if you think about this technology that I'm talking about, where we're actually using temperature changes on the surface to infer what's happening beneath the surface in the process to try to identify flaws, this is a technology that you can actually apply in a lot of different modalities. So it's not just temperature measurements like I'm showing over here in this part that was manufactured by University of Tennessee, Knoxville, Uday Vaidya there, where we're seeing pockets of resin-rich material that eventually lead to embrittlement in those areas of the material. So we're able to see those flaws form during the process. You can also apply this idea to, as we heard the earlier speaker, to the manufacturing of carbon fiber using a different type of measurement, not maybe a thermal measurement, but in this case, a profilometry measurement, looking for imperfections in the geometry, in the form, for instance, of the precursor material here in carbon fiber. Or you might be able to use machine vision to actually look for changes in fabric that might suggest there's wrinkling or there's fiber pullout in those fabrics. And you can use machine vision in order to identify those in process. So it's this basic idea of taking data analytics, taking what we can do to quickly analyze data, maybe using physics-based models coupled with the data we're observing to actually go back into the process and identify the formation of the flaw, and ultimately use that information to either design a better process that avoids those flaws from forming, or actually use that information in real time to control the process to reduce the potential for flaws forming. So that's the basic idea of what we're working on. Happy to take any questions. Again, appreciate the opportunity to talk with you.
Thanks, Doug. So it's always love listening to you talk. There's never any doubt about your enthusiasm for the subject matter. So appreciate that. And we do have a question that was posed, and it goes back to your detection method. But can you compare the reliability of your IR detection versus CT scanning? So were you able to take, for example, a panel which you discovered a flaw in via IR and then verify that through CT?
Yeah, so that's a great question. So we have not compared it with CT, but we did with ultrasonic inspection. And we're certainly able to see, the correlation in terms of location and generally the size of flaws. The other thing I would point out is that it's actually interesting and I think a really good question for a lot of reasons. But another thing to point out is that, what you're seeing with something like ultrasound or CT scan, typically you're looking for, voids in the material. You're typically looking for that high contrast area. So if you have a void, you're able to see the presence of that flaw. But what thermal imaging is looking at is actually something slightly different. It's looking for a change in the material state. So you could not only see voids, actually areas of the material where there's a gap that would change the nature of the heat transfer that's occurring. But you could also see, for instance, areas of the material that aren't properly cured that would lead to a reduction in properties. So I would just say, in some ways, this idea of using thermography during the process to look for flaws that are forming is similar to what we do after the process using techniques like CT scan or ultrasound. But in some ways it's different, because what you're actually looking at is the material evolving, and you're tracking that evolution. And so if the material doesn't evolve all the way, if the properties don't develop in the way that you would like them to as the process engineer, you can potentially spot that as well. So even if it's not a void, it might be a material that you're not happy with, and you can identify that by virtue of the fact that the process didn't go the way it was supposed to. So hopefully that answers your question.
Okay, so scale. What's the how large a part could you scale this to? We showed the wind turbine blade, 107-meter wind turbine blade. Would you just put repeating cameras like they do repeating laser projectors down that length?
That's exactly how we're envisioning it, having talked with you and Derek and Steve and others. But the idea would be to stitch those images together, those thermal images, by essentially piggybacking on the equipment that's already used. The advantage, of course, is it's full scale, it's line of sight. So as long as you can get line of sight of the mold, you're able to utilize these images. The thing I would say also is you would have to do some thinking around how you select your cameras. So you'd want to make sure that you have enough pixels, enough pixel density, so that if you have a certain flaw size that is unacceptable from a design standpoint, you would want to make sure that you span that flaw size, that minimal acceptable, maximum acceptable flaw size with enough pixels in order to ensure that you've got a high probability of detection. And that would be a matter of picking the right camera, but also picking the right distance that you are imaging the material, right? Because the closer you get, the more pixels you put on the surface.
Hey, you and I have kicked this around a little bit before, but when we talk about thick structures, and predicting the internal temperature, obviously if you're trying to control exotherm and so forth, big areas aerospace where you might be carrying a wing skin inside an autoclave. Can you actually harden these or find a way to do that imaging in the environment of an autoclave with that pressure and temperature?
That's a good question. We're thinking about that. Certainly you can harden them to some extent. You can actually buy cameras that are themselves hardened to different environmental conditions. But I'm not aware of a system that will go into that particular environment. So, what we've been thinking about are ways in which to both, look at hardening the instrumentation, but also what could you do with other technologies that don't, that might not require the same access that you need for the camera. So, could you potentially open up a window in the autoclave that withstands the environment that the autoclave puts the material under, but gives you line of sight access, through some sort of window. So we've looked at this this kind of approach to give us line of sight access without having to withstand that environment, to see if we could use today's technology. But
perhaps
it's
a clear window or a clear box or something.
That's absolutely. So you see this sort of thing, for instance, in gas turbine engines and in internal combustion engines, where you have combustion happening. You'll see test engineers design an engine block that essentially gives them access to actually watch the combustion process occur, and they can actually watch the mixing of the fuel, and they can also watch the temperature changes during combustion by opening up a window to study efficiency and these sorts of things. So they do it for the same reason, because their technology can't survive in that environment, A, and B, they don't want to interfere with the measurement itself by putting sensors inside the combustion chamber. So we're envisioning a similar approach where we don't want to interfere we don't want to have to harden the instrumentation. So what could we do to essentially open up a window, just like you said?
Okay. There's a good question here, and I think, might be, a good one for blade testing, for example, is could this have application in large scale structures, fatigue testing? In other words, stress concentrations generating mechanical heat during fatigue. The hysteresis heating, for example.
Yeah, no, it absolutely has. And we've actually demonstrated that in both metals and composites and looked at other types of machinery as well. For instance, meshing gears. So any place you see, cycles and the material cycling, sort of exhibiting both changes in local stress strain field, but also those changes bringing about local changes in temperature. These are actually very good. And thermography has been demonstrated in that context, by NASA's done some nice work demonstrating that, and plenty of gear train manufacturers have utilized it as well for looking at damage, for instance, due to cracked gear teeth and this sort of thing. So absolutely, it would be it could be used again in testing very large parts and fatigue characteristics of those parts.
Great. Okay. Before we'll let you go and we wrap up, integration of these technologies with machine learning, artificial intelligence seems like perfect fit.
Yeah, no, and in fact, common filters were artificial intelligence before artificial intelligence. So, in a sense, right, Bayesian techniques learn just like artificial intelligence, neural networks or deep neural networks learn. So over time, you take in more data, and the idea is just not to take in more data. It's to glean from that data something that you haven't seen before, to build a better, more accurate model, like we were doing, for instance, for temperature estimation, and to do that in a way that's statistically significant, so that you're driving down both the error in the estimate, but also your variance, your standard deviation in that estimate. So absolutely, this is a good fit for utilizing a range of technology. I would say that as in most techniques where you're combining, physics-based modeling with measurements, what you want to try to do also, right, in addition to just throwing neural nets at the problem, you want to use as much as you understand about the physics, because as engineers, and we talk to the industry partners within IACMI, they understand so much about the process, about what's happening to the material. And so I would say, coupled with the advances in data analytics, is the knowledge that you can capture by talking to industry experts, people that really understand these processes. Because if you can take that and apply it along with machine learning, you have a much better overall method for interpreting what your data is telling you. You probably don't want to just go in and throw AI at the problem and not utilize what you as an engineer understand about the process. But it's absolutely a good fit. And there are lots of examples that we've explored in that area and that others are exploring too.
Thanks, Doug. Appreciate that. I want to say thanks to all of our speakers. If you can close your screen, Doug, I'll show a couple of final slides. Just want to show upcoming dates. So our next event will be Tuesday, June 22nd, and then we'll do this again in July, August, September. In October is our fall members meeting, so we will not have one of these webinars, but we will actually do some innovation insights sessions at our fall members meeting, and then we'll resume again in November and December. All of those are noon to 1 o'clock Eastern time, whether daylight savings time now, and by the time we get out there in November, we'll be in or December, we'll be in standard time. But again, I want to appreciate all of you attending today. We've recorded this session, and we will send you a link to that recording as soon as we have that recording downloaded and available. Again, thank you very much to our speakers and our attendees, and we will see you next week or next month.